Hello, welcome to the first lab on the third part of the chemometrics course on the multivariate analysis. And today we are going to get more hands-on how to do modeling with multivariate data. And like in the lecture yesterday, we are going to look or use multilinear regression, and we are going to build here more a strategy about how to generally treat multivariate data for modeling purposes. And we are going to do this on the example of a paper by Kao and co-workers from metabolomics in 2015, which was handling the retention time predictions for hydrophilic interaction liquid chromatography and mass spectrometry applications. So the need for retention time prediction comes from the non-targeted analysis, where we are trying to identify as many chemicals as possible based on their mass spectra. However, to one mass spectra, mass spectrum, several chemicals can correspond. So to try to reduce the candidate list, the possible structures that can correspond to this one mass spectrum, we can use additional information collected during the analysis. And when we couple liquid chromatography with mass spectrometry, then one obvious possibility to reduce this candidate list is by using liquid chromatography retention times. And this has been quite an important topic for reducing the candidate lists in non-targeted screening for a couple of years now. And is widely used both in research, but also in practical monitoring. For example, in Sweden, non-targeted screening is used both by EPA as well as many laboratories doing water screening. And they also implement the retention time predictions to make sure what actually we have in our waters. So here we are going to use this nice example for building a workflow on how to predict retention times and how to also validate how good our retention time predictions are. So we will be doing both the model training and then the validation. And we are going to go through this step by step. So in this paper that we are going to use as basis for our modeling exercise today, there is a nice supplementary information which contains all the data used in the paper. This is a very good and very useful strategy that people who do chemical modeling should follow. And here it has been very nicely done. So this file comes in a comma-separated value format, so .csv file. And most of you should be able to open this for viewing in Excel by just double-clicking on it. Or if not, then right-click, open, and choose Excel as a software to open the file. When you open this, you will see that this dataset is really a multivariate dataset. It contains multiple columns with different information and also different rows. It altogether contains 116 chemicals in this dataset, for which the retention times with the helichromatography have been registered. And before we start processing this data in Excel, we should a bit look at what we see here in the data set. What are the reasonable columns? What should we keep for the modeling? And what is any background information for us? So first we see that in the first column, there is something which is called CID. And this is the chemical identifier from the PubChem database. So this does not describe the molecules as such. It is an identifier which has just been used in the database to link different properties together and to have one set of parameters that can be linked from different tables, so that one chemical does not get repeated in the data set. Then we have also compound name here. So these are not UPAC names, so they are kind of intuitive names, which are good for us to later look at which chemicals have been predicted how well and to analyze our data. Then we also have SMILES representation of the chemicals. So SMILES is a representation, text representation of the chemical structure, which is extremely often used to compute different properties of chemicals from its structure, from its simplified structure. So this is usually a 2D structure, so it's not 3D optimized. And it contains the information which carbon is linked to which carbon. Is there a double bond? Is there a single bond? Is there any branching? So from a SMILES, you can draw the structure on paper. And from a structure, you can draw a SMILES. However, SMILES is not unique. So we have to just keep that in mind for later modeling exercises. At the moment, we know that the SMILES is here, and if you want to check the structure, if you don't know by the name how the chemical exactly looks like, then the SMILES is there to check up the structure as well. Then in the next column, we have retention time. So this is what we will be modeling here. So we want to predict the retention times, and these retention times have been given in minutes. And then we have a bunch of different properties here. For example, first one here, X log P3 is a calculated or predicted log P value for these chemicals. And then there are also bunches of other parameters that you should try to look a bit up what they are doing, especially later when they turn out to be important in your models that you will be developing today. For example, here is NHBAC, which is the number of hydrogen bonds that the molecule can accept from the other chemicals or solvent molecules surrounding this chemical, or the number of hydrogen bonds that it can donate to other chemicals. And when we scroll here, we see a number of different parameters like this, which all describe the structure of the chemical. And we might also notice that some of them might be somewhat similar to each other. So first in the beginning, we had an X log B3 here. But we also have here a different log P value here, which is slightly different in its value, but also describes the polarity of the chemical. So we have to keep here in mind that we might have chemicals, which we might have here descriptors which describe similar properties of the chemical. Good. So after we have looked a bit on the data, on the descriptors, what we have here, we are ready to go and start reading in the data in R. Okay, so now when we know what our data is about and we have it saved in a folder that we know, we can start processing this data in R. And I have here a R Markdown file open, which you have been using already in this course before. And the first thing that we need to do is actually to load the libraries that we are requiring for the data processing. You might need to install a couple of these libraries here. I have them all already here, so I can just import them. So the first one, which we definitely always need, is a tidyverse. So this will help us to write a good, concise code, which is easy to read. But we also need special modeling packages. So first of all, we will be doing here automated cross-validation, and all sorts of modeling is very well represented in the package called carrot, like the carrot. And you should actually go in and try to see a vignette of the carrot library. So when you open in Google and you just Google carrot package R, then you will end up on a carrot package vignette page, which looks something like this. This is a very good example of a vignette for an R package. It's really very thoroughly described, and you can really use this as a guide to use this package, but also to generally learn yourself about different things that can or should be done during the data processing with your data. When you look here on the left-hand side, then you can see here different chapters, and these chapters introduce all of the possibilities which are in carrot. But they also give you some background information, why and what sometimes something could be done. So for example, there is a preprocessing chapter here, and you can read here about different functions which are present in carrot, as well as you can see good examples here. And it really reads as a good side reading for doing the modeling. So you can really see here what it is doing and why it is doing. And we will be very soon actually using some of the functions from here, including the near zero variance one, which we have just in front of us here as one of the first processing variables. So once we have carrot, we also need two additional more libraries, and one of them is called CA tools, which we will need to do some random splitting of the data for the validation purposes later. And the last one is the one which we need to do multilinear regression with the stepwise selection of the variables, and this is leaps. So if we have these, if you have these packages installed, then we can also load them. So Ctrl+Shift+Enter will run us this churn of the markdown code, and we can install the packages. We will also get back information. For example, I got an information that it additionally is loading another package called Lattice and ggplot2. And ggplot2, for example, is loaded automatically with tidyverse, and we will be using this for efficient and beautiful visualization of the data later. And also I got information about which versions of the packages were loaded. So you should be getting something similar. You might get slightly different numbers here because we might be working in different versions of R and with different versions of these packages. So now when we have the libraries read in, we can start reading in the data as well. So our data was as a CSV file. So I suggest to use read the lim function, also from one of the tidyverse packages. So when you have library tidyverse loaded, then you can automatically use this, read_the_lim. So this will automatically give your data set as a tibble. Tibble is a data frame which is fully tidyverse compatible, so it's very easy to handle, and it doesn't act sometimes comically, so it's very concise and works very well. So I suggest to use the read the lim. The first thing that we see when we type read the lim, we see what is the file location, where we need to specify, which we need to specify here. So if you have your directory where your CSV file is as a working directory, then we can just type here in the name of the date of the file. So I have my working directory specified, and I can just write that this file is cow 25 2015 underscore SI CSV. Now, when I have finished typing this, I can read from here further that there are also other parameters that we can specify in the read the lim command. For example, we can specify the lim. This is the mark that is used in the CSV file or text files or tab separated files, anything that you might be wanting to read in. All of them can be read in with read the lim. What is separating between the different columns. So in the Excel, we automatically see columns, but most of the data is actually not kept as Excel, but as some kind of text files. And in these text files, how to know where one column ends and the other one and the text for the other column starts, there are markers for that. Usually, read the lim is very good at guessing what your marker is, but if it is not, then you want to do the then you want to specify this. So what we can first do is that we can just try to use the definition like this. So I'm just executing this, and voila, my data got ready. So R is telling me now that I have 116 rows, as many as there were chemicals in this data set, and 35 columns. So these are all of the variables. And it also tells me which types of columns there were. So there were 2 columns which had the textual values, so character. These were compound and smiles, and this is what we also saw already from the data set, that there were 2 columns saying, giving information about which chemical it is, the name and the structure as a smile. And then there are all other 33 columns, which the read the lim guessed are double variables, so that means continuous variables. And this here we have to pay attention that actually most of them really were continuous. But the PubChem identifier, CID, is not actually a continuous variable. So we have to still keep that in mind. We can also look at our data by going here at the environment and clicking on the data set. And from here, we can see our data like we had also it in Excel. So we have the same columns here, very nicely separated. And when I hover over one of the column names, then I can also see a description of this column. So I see it's column 4 and it's numeric. So we didn't specify this, what type it is, but read the lim did a very good job figuring out what it is. Now, some of you might have that this does not work properly. So you might see that you have only one column where all of the information is jammed together. In this case, you need to go back and specify what is the delimiter in your data. So how to know what is the delimiter for your data? One of the options is to go back to the data and look at this in a text file. So when I am opening my CSV file, now not by double clicking in Excel, but if I am opening it with a notepad, for example, then I can see that my data looks something like this. And I can see from here that what before were different columns now are separated with a comma. So this means that in my case, the columns are separated with a comma. In addition to the separators of the columns, it might also be good to know what is the separator of the decimal points in your data. And this you can see when you look at individual values here. So for example, I have here a retention time of 10.61. And we can see that in my case, full stop is the decimal separator. So some of you might also have that ReadyLim did not figure out what is your decimal separator, and then we need to specify this as well. Good. Let's try to do that. So when we go back to our R, so here in the delim, we can say what is our column separator. So in my case, this was a comma. And if we need, in cases where these columns were not identified as numeric, and you don't see here full stops, but you see here commas, for example. This might happen if you have a Swedish version or some other version of Excel, which usually handles with commas as decimal separators. Then you might here have something weird here if Excel converted your data while we opened the CSV file. Generally, when we are provided with a CSV file, CSV files do not change unless we overwrite ourselves this. And this is very good because this actually allows sending these files and sending R codes between different computers, which are operating in different languages. So if we need, we can also identify what is the decimal separator, and this is called local in R. And we can say that the local is local, and now we have to say what exactly we are specifying. We can specify here different things. We can specify the language of the names or the time format or anything else, but we want to specify here potentially the decimal mark. And we see that as a local, the automatic decimal mark is a full stop. So if you need to put in what is your decimal mark, so potentially a comma. But I have it in English and as a full stop, so I just keep the full stop, which also is a default. So in my case, I'm having all the standard settings. I would not need to actually have these two lines here, but some of you might need, depending on what is your language settings and decimal separators and decimal separators and the column separators on your computer. Now, when we all have successfully read in our data, we can also look a bit more detail on our data set or to our data set. And one of the things that we can do is we can just scroll through it. And one thing that we will start noticing is that for some of the columns, we will have here these NAs, so not availables. And we see this for multiple rows here on different columns. And the problem that we will face with the NAs is that the lines which have not available values cannot be used for modeling, at least the ones where the NAs are in the columns which we actually want to use for modeling. So this means all of the columns retention time as well as the descriptors, so xlog p3 and so on and so on. So one thing that we should also actually do is to remove the rows which don't have all of the values available. This is a good strategy as a starting point. In some cases where you have very many missing values in some specific columns, you might need to use a different strategy. And we will actually be using this strategy later in this course. But in this lab, we have a few compounds which have multiple missing values. You can explore this in detail in peace and calm. And we will cope with this problem by just removing the lines which contain these missing values with an NA omit. And I'm going to pipe this directly after my reading in data. So I have them as two put together commands. And here important thing is pipe. So pipe means that I can put multiple commands together, and it is a percentage sign larger than percentage sign. And you will have this functional in your R when you have tidyverse package loaded. So this will allow us to do a lot of fun and very concise code writing. So when I have this here, I will reread my data in. And what we see from here is that the message we got when we read in the data is exactly the same. It still is that there are 116 rows and 35 columns, with 2 columns being textual and all the other 33 being numeric. But when we look at here in the environment, then now we see that there is 114 rows left. So this means that these 2 chemicals for which we could see the not available values for the X log P, they were removed. So we lost at the moment 2 chemicals from our data set. And actually, on the relative basis, it's not such a big loss in data processing. It's very often that we unfortunately don't have all of the descriptors for all of the chemicals, and we need to do some kind of a smart strategy. And if this is such a small number, like 2 chemicals from 116, then removing these chemicals, their lines, is quite an okay strategy. We don't lose so much of an information here. So with this, we have the data read in successfully, and we can start with the first pre-processing before the modeling. Okay, so now when we have the data read in, we can start with the pre-processing. And with the pre-processing, we will be doing a couple of different things. So the first thing is that when we were looking through the data set, we saw that there are a couple of columns which contain quite similar information. We saw that there were 2 log P values, and actually there can be even more columns which are correlated with each other. In the case of having correlated variables in the dataset, we are facing a potential case that we are overfitting our model to the data that we use for training, but this might not give similar, and this might not give similar performance on the real application or even in validation. So to mitigate this, even before we start any modeling, we should remove the correlated variables from the dataset. To do this, we will be using the observing which variables are correlated with each other, and then we will be removing the highly correlated variables. So even before actually we can do this, we need to organize our data a bit. So the thing is that we want to do this correlation investigation only for the columns which are our descriptors. So the ones which we'll be using to predict the retention time. And because of practical reasons, we want to move the other columns, which are like an additional information, into the end of the table of the data frame. And this is just for practicality so that we can remove the highly correlated descriptors most easily. So what I'm going to do is that I'm going to say that I'm going to modify my data set. So it's still going to be called data set, and it starts from the data set that we have now loaded with 114 rows and 35 columns. And I'm going to modify it by relocating the columns. So I'm saying that it's the data set what it is going to be called. It starts from the data set, but with a pipe, I'm going to say what is the operation, what is the function that is going to apply to this tuple, to this data frame. And the function that you can use to relocate the columns is called relocate. And in relocate, we can first specify which are the columns that need to be relocated. So here, in the data set, the columns which are not descriptors are the first one, CID, so the identifier of the chemical, also the name of the chemical, its structure as a SMILES, and also retention time, because this is what we want to predict. We don't want to remove this column definitely. This has to stay in our dataset. So we move forward the ones which are not our descriptors to the end of the dataset. So here I'm going to specify in the list, so C and the brackets, that it's going to be seed, so the first column. It's then going to be also compound. This is how the second column with the names was called, and also SMILES. And last but not least, also RT, so the actual retention times. And I'm also going to say that I want this to be after the last column. So they are going to go to the end after the current last column. And when I execute this, visually nothing changes. My dataset still has the same number of rows and the same number of columns. But when I click on it and open it again, then I see that now the X-log P3 is the first column, and seed, compound name, SMILES, and RT are the last columns. So with this, I have reorganized the data, moved the order of the columns. And this here is useful for removing the correlated descriptors that we will be doing in a second. So once we have reorganized the columns in our dataset, we can start looking and finding the highly correlated variables and later also removing them. So the first thing that we want to do is we want to calculate the correlation coefficients between the different descriptors here. And I am going to call this matrix where we will be having all the correlation coefficients, a correlation matrix here. And we can obtain this by using a function COR from the statistics package. This is one of the packages that you would be automatically having. And you can here specify, or should specify here, what are the descriptors for which we want the correlation to observe. And the best way to do this is to say that we want to observe it for the columns in our data set, but we don't need that for the 4 last columns, because these are not our descriptors that will be used in the model. So we remove from here the columns with the seed, PubChem seed, name, SMILES, and the retention times. And for this, I'm going to pipe the data set with a select function. And in the select, I'm going to remove the columns which we don't need. So to remove, I type a minus sign. And because I'm going to use multiple, I'm going to remove from the correlation study multiple columns. I'm going to make a list of these column names. And here I'm going to put the seed, the PubChem identifier, the compound name, compound was that called, SMILES, and also the retention time. So the retention time we definitely don't want to remove from the data set. It's the one which we are going to use to train our model, and therefore we are going to have this in our data set. And when we execute this command, then we will get the new matrix here coming up. You can see that it looks a bit different because this now is a matrix, it's not the data frame. But still, we can look at it. So when we open this in our viewer, then we see that here as columns, we have the different descriptors and the different descriptors also as rows. And when we go by the cells, then for the first column, first row, it is the correlation coefficient of x log p3 with itself. So of course it's 1. For A pole with x log p, it is 0.63. For the B pole, it is minus 0.02. So each of the cells corresponds to the correlation coefficient between these, between a pair of two descriptors. So now with this correlation matrix at hand, we can start removing the variables which are highly correlated with each other. And for this, we will use a find correlated function from So now with the correlation matrix at hand, we can also investigate which parameters are highly correlated with each other. And this can be done with a function find correlation from the caret package that you installed and activated before already. And I am going to collect this all into a variable called highly correlated. And the function itself is find correlation. And you see it comes from the caret package. And now the first thing that this function wants is an input as the correlation matrix. And I have here updating my correlation matrix, and I am using this correlation matrix as using my naming here, and now also using this correlation matrix as the source for the correlation coefficients. However, also we should add here what is the cutoff. So what is the value over which, absolute value, over which we are saying that the correlation between the two variables, two descriptors, is too high. So we specify a cutoff, and this is 0.75, for example, in my case. This can be somewhere between 0.6 to 0.9. It takes a bit of a feel for the data set to see how many variables are removed. The usual values are somewhere around there, from 0.6 to 0.9, usually 0.7 to 0.8. And when we execute this now, then we can actually see that we got a list of 25 numbers here. So when I'm in my console asking for the highly correlated, then I get the list of values. And this list of values is the list of columns that will be removed based on this similar high correlation. So a correlation coefficient higher than 0.75 or lower than -75. So this is the absolute cutoff value. So here are the column numbers, but now we actually need to remove these columns as well. And for this, we can use the data set, redefine it again, say that it is still the data set. It will be called data set and it starts with a date from the same data set. But we will remove the highly correlated columns. And this we can again do with a select from tidyverse or actually deepler, which is a sub-package, part of tidyverse. And we can say that we want to remove all columns based on their numbers. So how, is it the first, second, or 29th of the column? With a minus sign, and we say the highly correlated ones will be removed. So now I got a warning from the removal of the highly correlated variables. So this is like a warning or a note that it might be ambiguous to remove these columns like that, but the function actually still works. So when we go to the data set, then we actually see that now we have only X log B3, acceptance of hydrogen bonding, donoring of hydrogen bonding, and a couple of more, 3 more descriptors left in the data set, and all the information about the compounds to which these data points belong to. Here it is important to think back a bit, and here we can understand why we could justify the moving of these compound identifiers. So the PubChem seed, the name, the smiles, and also retention time to the very end of the matrix, of the data frame where our data is. So when we did that, then we could very easily remove these columns from finding the highly correlated descriptors, so that the column number, so the location of the column, didn't change compared to the data set that was originally there. So this is just to not remove the wrong columns and to actually make sure that the column number in the highly correlated matrix is actually corresponding to the column position which we want to remove. Here comes also the first task for this exercise class, and this is to go into the find correlation function and find out what happens if 2 variables, 2 descriptors are highly correlated to each other. How does the function know which one to remove? Because if there are 2 which are correlated, we only want to remove one of them, to not remove all descriptors that carry the same information. We want to remove all but one, so we want to keep one of them. So how does the highly correlated function know which one to keep and which ones to remove? So now when we have the correlated variables removed, and we have only the variables, the descriptors, which really carry significantly different information from each other left in the data set, we are ready to start splitting the data. So we want to use the part of the data to train the model that will predict the retention time. But part of this data we want to keep aside so that we can use it to evaluate actually how well the model has learned to predict the retention times. So what we will do now is that we will split the data into validation and training data, and we will do this by random splitting. So first thing that we actually need to do is that we need to make sure that the splitting is reproducible but random. So we will use the randomization algorithm from the CA tools package, but because the random number generators behind the packages are using time as an input for generating random numbers, the randomization will be different now in 5 seconds and in 10 seconds. This is a bit of a problem if we want to compare the results that we get now and in 3 months with the same data. So to make sure that these results are the same now, 5 seconds and in 3 months, but also between my computer and your computer, we need to initiate the randomization with a seed. So we need to give the computer a small seed that it will put into its randomization algorithm and create the random numbers. So this means that we will be able to create a random split, but this random split will be the same now and later. So to do this, we use a set seed function from the base R, and as a seed we just give some kind of a number. In this course, so that we would all get similar results, I suggest that we all use here 1, 2, 3 as an input. Theoretically, you could have whatever number. This is the seed number, so when you have the same number and the same data, you will get the same split. It's also important that you specify this random seed every time when you are using some function which uses random numbers. Splitting is one of them. So now we want to do the splitting itself. To do this, we are going to add one column to our data frame, which says if this compound will be used for training or for validation. So I am going to add to my same data set. So it's still going to be called data set, and it starts from the existing data set. I'm going to add a new column. I'm going to do a pipe here, and I'm going to add a mutate. And mutate will allow me to change columns in the data frame or add new columns. So the first thing that we need to define here is what is the name of the new column if we are creating a new column. And I am going to call mine split because it will be telling me if we have splitted this data point into the training set or into the validation set. To now do the actual split, we are going to use a sample split from CA tools again. And when we do this, when we select this, we can see what are the inputs that the sample split is requiring. So the first thing is a y, which is a vector, which length will be used as an input to know how many random trues and falses will be generated. So we want this vector to be as long as is the number of chemicals in our data set. So we have 114 rows, and we can use actually here any column from the data set to as an input to get this length of the column. Now I'm going to use retention time so that as this is one of the columns in my data set. And after this, we also need to specify split ratio. This is how many of the chemicals will be going to the training set and how many will be going to the validation set. So usual strategy is to use 80%. If we have very large data sets, then we can use actually more for training and less for test for validation. Then we would still in the validation have multiple hundreds of compounds. Here it's not the case. Here we have 114 chemicals, so we can split with a very traditional 0.8 ratio, so 80-20 ratio. And when I'm executing this, sorry, I first need to execute my set seed, and then I can also execute this. And my data set now got a new extra variable. We see that number of columns increased. So when I go to my data set, I can see that I have now here a new column called split, which has a bunch of trues. So it has 80% of trues and 20% of falses. So these trues will be indicating us that this will be used for the training of the model. And the falses are the ones which will be used for the validation of the model. In cases when we would be testing different machine learning models, not only multilinear regression, we would need to follow up here with an additional splitting. We would need to additionally split if a chemical is belonging to a training or a test set. So in cases when we develop multiple different models, we train a training set, we compare all the models on the test set, and we evaluate how well the selected model, the best model, is doing on a validation set. In this specific case, we have been deciding from the beginning that we will be using multilinear regression, and we are not going to develop any other models. So we don't need the test set, and we can use the whole training set for actually training the model with cross-validation, of course. So the next thing up, we are going to set up cross-validation. Okay. So now when we have the data split for included in the column for the training and validation set, we can also set up the cross-validation method. And cross-validation we will be using within the method training, so that during the cross-validation, we always set aside part of the data that will be used within training to evaluate how well the method is performing. And this is going to be done also a package with a function coming from a caret package. And we are going to first set up a method for the cross-validation, and I am going to call my method a fit control. So this is just the name of the method which I'm going to use for the cross-validation. And the method or the function within caret that can be used is called train control. Train control from caret. Good. From here, we can see when we go on this method here in R, what are the parameters that can be specified for the train control method. So when we want to do repeated cross-validation to tune the parameters and select variables in the multilinear regression, then we need to specify as the method the repeated cross-validation. So we say that the method is repeated cross-validation with a CV. There are also additional possibilities available, different methods, and we feel free to go and explore these from the caret package page or from the help here in our studio. And the next, actually also the question for the homework will be about exploring what they actually mean and which options are available for there. Now, when we have specified the method, then repeated cross-validation, of course, can also be carried out in different ways. For example, we can split the data into different portions. So we can split it into 5 different portions, or 2 portions, or 10 portions, 20 portions. So definitely we need to also specify here into how many sets we want to split the data for cross-validation. And this can be done by specifying the number here. And let's say I want to do a 5 set splitting, so I specify the methods as 5. And also, it is a good practice to not just do it once for 5, but also repeat this by reshuffling the data and doing new again the splitting into 5. So we can also put it repeating. And let's do a repeating of twice here. So this is the important aspects for setting up the method for repeated cross-validation. And once we have this set, we can run it. And what we see here after running this is a new data showing up here on the environment. And when we click on it, then we actually see the method. So this is not a data frame. This is a method of different parameters, which will be used then during the model training to choose the parameters in multilinear regression. And in other methods, this will be used to tune the hyperparameters. We will be looking more into this in the next classification and regression classes. So in short, this is a description of how the model is going to be trained. And we changed here only which type we are going to do, which number and how many repeats is going to be used. There are many other more aspects that can be changed as well. So you can really customize how the model training will be done here with the train control. Okay, so with the training method set, we can now actually start training the model. And the first thing we need to do, we need to again tell our computer the seed which will be used in the random splitting. So the fit control contains the information that we want to do a cross-validation, and in cross-validation we will be splitting our data into 5 sets. In each training of the model, 1 of the set will be left out and 4 of them will be used to train the model, and the left out set will be used to evaluate the model. So now to actually train the model, these sets, these 5 sets will be created, and this will be done based on random splitting. So to actually again initiate a repeatable randomization, we will again set the seed, and I am again going to use 1, 2, 3. Now to train the model in caret package again, there is a function called train. And we need to give first a name to our model that we are going to train. And I am going to, out of habit, call it a regressor. A regressor because it is a regression function and it will be predicting a continuous variable. So it is, I call it a regression. And to now train this regressor, this model, we need a train function from caret package. And this will give us a model and a set of parameters which were tested and how they perform. So it will contain a lot of information. But before it will do this, we will need to tell it a bit of information. So the very first thing that we need to do is we need to tell what kind of a model it is a training. And in R, this is usually written as first specifying what is the predicted variable, and then inserting a tilde and saying what are the parameters that it is going to be predicted from. So theoretically, we could be writing here, for example, x log p plus some other parameters. Where the parameter 1 and parameter 2 would be the names of the columns which we want to put into our data, into our model potentially, which need testing if they fit there. However, in multivariate cases, there are usually too many columns to specify them one by one. So therefore, there is an option to say that all columns besides the predicted variable will be used for training. So we can use this option, but we also need to specify what is our data frame, where these columns will be taken. So we say data, and mine is called dataset, but in the dataset, I have a couple of columns too much. So I also have the information about the chemicals there. So their PubChem seeds, their compound names, and their smiles. And I need to take these out. And I also need to make sure that I am using only the data, which is my training set. So the first thing that I'm actually needing to do is that I'm going to use a filter function. And I'm going to filter only the lines which have the split value true. So the split values which we assigned before when we were splitting the data into training and validation part. And when I've done that, I also want to take out the columns which are not useful to predict the retention time. So the identifiers as well as the split column. So I will be using a select here from DeepLearn again, a subpackage of tidyverse, and I'm going to take out the columns with the PubChem identifier, with the compound name, and also smiles, and the split is going to be taken out as well. Good. Now here I have my data specified, and the formula that is going to be fitted with the train function is also specified above here. But I also need to specify what kind of a mathematical model I am fitting, and this is called a method. And when I am using multilinear regression with stepwise selecting of the descriptors, then one of them is GLM step bike. So if you want to know which kind of mathematical models are available there to train a model in R with the Caret train package, then we can go back to the Caret's Vignette and we can try to read from here. So in the here in the summary, we find chapter 6, which is available models. And when we look from here, then we see a long list, 238 different models that can be used, can be trained with the train function. So these are all the mathematical models that can be used to model our data. And you can see here different things. You can see a general model name. You see also what is this method called. You see also what type of it is. Is it a regression or is it classification? You see what library it is coming from, and you see from here also tuning parameters. So what are the parameters that can and will be optimized during the train? And we can, for example, look at GLM step IKE, which stands for Generalized Linear Model with Stepwise Feature Selection. And it suits both for the classification and regression. And it comes from a library called MASS. This is a library that you all actually probably have automatically. And you interestingly don't need to load this library. Actually, I suggest you not to load this library because loading this library might make some of the other functions from tidyverse not work properly. So you need to have it installed. Pros probably have it installed, but don't activate it, don't load it. And in the last column, you actually have tuning parameters, and for stepwise linear model, it is none. This means that there are no parameters, no hyperparameters. The train function will, instead of tuning some hyperparameters, actually do the stepwise selection of the descriptors for this model. We will go into the hyperparameter part more in the next lectures and labs in this course. At the moment, we just know that there aren't any in the multilinear regression that we are doing. Good. So once we have this specified, which math is going to be used, we also need to specify what is the training strategy. So we need to actually tell that we want to use this repeated cross-validation, and it's going to be 5 sets and repeated twice. So we specify what is called TR control here, and we use the same name as we put it to this method here up or in the last term. So this is called fit control. Yeah, here we go. This is here. Okay, so now when we have the train function written, we can just execute it and actually train the function. So when we start, when we execute this, we see training starting and going on. And we also get an outprint from what the training did. So in below here, we see the training outcomes in all of these 5 repetitions, which have been repeated twice. And we see that the backward selection, which is used here, is how it is working. So first, it starts with a model that includes all 6 descriptors to predict the retention time, here denoted as the outcome. And we see here also something which is called an information criteria IC. And we can see how this is changing when different parameters are being omitted from the model. So trying to figure out which one of these descriptors is the least important or least useful in this model. And here we actually see that the least important one has been determined to be the top shape, the one which has the lowest IC value. And this is the one that is not then in the next step included. So this is kicked out, and the new multilinear regression with just the 5 parameters is trained, is fitted, and it is compared with even simpler models where either one of those 5 parameters is removed. And here we see that in the next step, the parameter that gives least information, that is least needed, is the VC3. So iteratively moving on, this parameter is removed from the model is refitted, and again compared with even simpler models in the next step. And this continues here until the model from which none is removed has the lowest information criteria, this Ike value over here. This means that if the next parameter would be removed, a lot of significant information will be lost, and it is not statistically insignificant to remove this next parameter. So in here, the model fitting stops after removing 3 variables and keeping 3 variables here. But this was now done just with 4 of the sets used for the model fitting and keeping 1 for evaluating all these models. So this evaluation was done with the 1 set. Now, training continues, and the set which was used for evaluation later is put back into the data, and one of the sets that was before used to train is left out and used for evaluation, and it all starts over from here. So again, we start with a model with all 6 variables, and iteratively each one of those descriptors is evaluated. The one which gives least information is emitted, new model is fit, and then is compared with even simpler models from which each one of the parameters is kicked out. And this is continued until we have done this for all 5 sets and repeated it twice, because after doing it for 5 sets, we are reshuffling the data and dividing it again into 5 sets so that we can do the training again. So this is what you can see here from the output of the train function, but you actually also get something very important, which is this regressor here in the environment part. And we can open this regressor by clicking on it, and we will see here a description of all of the things included in the regressor. And we will find from here information about what it is, what type of a model it is, and also about training. But we also find information about the final model. So, for example, from the method part, we see that it was a step GLM step Ike that was used to train the model. You also see from the model info a bit more about from which package it comes from. And from the results part, you can see for the final model how it was performing. What was the root mean square error? What was the R-square value? What was the median absolute error? And so on and so on. So you get the statistics here. And when you go through this, then you can here see different things. You also see, for example, metric here. This metric, this is the root mean square error. This is how the different models were compared to each other when each of the parameters were left out. So how this RMSE was changing. This is the default here in the train function. And in the final model part, you will also find the statistics for this. So you will see here coefficients. And when you all click that open, you see that in the final model that was selected after all this cross-validation. So cross-validation decided on which parameters are going, which descriptors are going into this final model. And then all of these 5 sets were put back together after doing that. And their coefficients for these descriptors in the model were obtained by fitting a model to all of this training data. And we can see that 3 of the descriptors were used: the X log P3, hydrogen bond acceptor power, hydrogen bond donor power, and also an intercept is over here. So this is how our final model looks like. You can now also look again at the training results and see how did the best models trained on each of the cross-validation sets. So for each of the 10 cases where the model was fit, which parameters actually ended up there, and does that somehow differ from what was found for the best fit model? Now, there are also additional ways to look at the results obtained with the training. So one of them is to ask to print the regressor. So when we print the regressor, we see a very small overview of what happened during the training. So first, it tells us again which type of model was fit to the data. It also tells us that we were using 91 samples. So these samples actually here means chemicals, so the number of rows. Though this is just the training data, as we with the filter function only kept the training data. Then we also use 6 predictors, so 6 columns. And it also tells us that inside training, there is no pre-processing. So we did the pre-processing ourselves before. The training doesn't include any additional pre-processing. It did resampling with cross-validation for 5 folds, repeated twice. And for these folds, the sample sizes were 72, 74, 72, 74, 72, 74. So this means, and so on. This means that in the first instance, the training was done with 72 data points, but 91 minus 72, so 19 data points, 19 chemicals were used to evaluate the results. Now, the sampling results over here, this also tells us what are the summary statistics. So what is the summary root mean square error, the R-square value, and the median absolute error. So how good is our method doing? So the root mean square error we can interpret as very similarly to standard deviation. So we can interpret this as on the 68% of the cases, the retention time, which is actually observed for the data, is plus minus 2.2 minutes or 2.617 minutes, different from within the limit of plus minus 2.17 minutes from the predicted value. Then in addition to this print function, we can also look at the summary. So we can ask it to show us the summary of the regressor. And this is very similar to what we could also see by just clicking on the regressor. So we can see here information about the different parameters or different descriptors in the model, their coefficients, their statistical significance level, but also about the prediction errors. So these deviance residuals here are prediction errors. So what was the minimal error? This means that how much lower was the actual retention time for the predicted retention time in the worst case. And similarly, the maximum is how much higher was in the worst case, the actual retention time from the predicted one. And then we also see here a bit about the distribution of the residuals below here. So this is where it is also an additional possibility to have a look at the results. And if we just want to get out the final model for example, later saving it, then we can actually also ask for it from the regressor and $sign final model. This is where we can also see. But if we want to apply this final model, we don't necessarily need to do this or copy these values, We'll see how to use this to predict retention times in just 1 second. So now when we have looked at our model and analyzed it a bit, then the next step is to do also validation. So actually make some predictions. And we are going to use here adding the predicted retention time to the data frame. So we start by telling that we are going to add to our data set a new column. So it's still going to be called data set. And it is starting from a data set. And we need to add here a new column with mutate. Use a mutate, and I am going to call my new column RT predicted or RT bred. So my column will have this RT bred, and it will be predicted for all of the rows there. So I'm going to do this prediction for all of the 114 chemicals, so both the validation and the training data. So we can also look at them side by side later. And to do the predictions, we need a function called predict from the statistics package. And this one's first is an input, an object, actually the model object. So we first need to tell it that it is the regressor, and it will find the right place itself. We don't need to specify anything more than just the name of the model that we have fitted. And then additionally, we also need to tell which data it is going to be predicting for. And so we need to say that new data is going to be the data set. Otherwise, it just does it for the training data, but we wanted to do it for everything in our full data set. So once written, we can execute this, and we automatically see that our data set gained a new column here. So it's now 12 columns. So when we go to our data set, we can see that the last column is retention time predicted, RT_bred. And we can look at the numbers visually, how they look like, but even better, we'll look at them immediately also graphically. Okay, so now to look at how well these predictions are made, we will use a ggplot. Strongly suggest to use this because it will be so handy to look at different things, color differently points, and modify how your graphs look like. So we are going to specify first what is our data. This is data set. And now in ggplot, there is no pipe with the percentage larger than percentage, but there is a plus sign that will bind different rows together. So after specifying the data, I'm going to specify which type of a plot I'm going to do. And I am going to do a geom point graph, which is then the scatter plot. For putting the data on it, how to put what goes on which axis, we use the mapping, and mapping takes different things at input. Here we will be using the aesthetics first, in which we specify what is on our x-axis, and it is always with the linear regression that the more accurate values will be going on the x-axis. So here the measured retention times will be going on the x-axis, and on the y-axis we will be putting the predicted retention time, so RT bred. And in addition to this, actually for the first try, don't need to have anything else. I can just execute this. And I will be getting a plot here with the retention time predicted on the y-axis and retention time actual on the x-axis. So the first thing I can see is that I have some correlation here, but I lack a lot of information as well. So here I have actually all of the data pulled together, both the training data and validation data. And I might actually want to pull them apart. So, okay, so now I can actually go back and modify my graph somewhat so that I would pull apart the different splits. And for this, a naturally good thing to do, simplest way, is to use a facet graph. This is a way to divide one graph up into different graphs based on one parameter in the data set. And I am going to do that based on the split, because this will be the variable that describes, in my case, which is the training set and which is the validation set. So when I implement this and execute, then I automatically see two different data sets, or two different graphs, sorry, on the data set. One for the validation, so where the split was false up here, and where the split was true, so up here. But now I have still a bit of problems, so I might want to try to make my graph generally a bit more beautiful, but I also could add here a line that shows us the perfect fit. So I can add something which is called a geom-ab line. So this is a straight line which takes as inputs slope and intercept or other parameters. But slope and intercept are very convenient to describe an ideal fit. So in ideal fit, the predicted values and the real retention times would agree perfectly. So we would have a line which has a slope 1 and 0, intercept 0. So we can write here that we want to put a line with slope 1 and intercept 0 here, and we can execute it again. Here we see now also this line added, and this helps us to now maybe visually analyze the results a bit better. How far are the points actually from the ideal lines? So we can visually see that actually the predictions do increase when the actual retention times increase, but there are some points which are maybe not so great. So maybe here we see that there are some points which are quite far away. So this takes a bit of digestion, which you can be doing once we have it all implemented. I also want to label my data actually a bit better, because at the moment I have just RT underscore pred and RT. I probably want to say which units they are. So I can also add a labels argument here, and I can say that my X label is retention time in minutes, and my y-axis is predicted retention time in minutes. And I might also want to remove this background, so we can also play around with a theme a bit. You can really define this yourself from scratch, but you can also pick from here. So for example, I can apply a classic theme here. So when I execute this, then I get a bit cleaned up figure with the two validation set and training set side by side, nicely plotted here. And I can try to draw from here some visual conclusions. Now, what we might, in addition to the visuals, do is to also calculate some of the metrics for both the validation set and the training set and compare these to see how good is the method before the model performing on the training data and on validation data. Are these performances acceptable? Is there any overfitting? What do we think about that? So to do this, one of the possibilities is to calculate root mean square errors, which are in regression tasks our best friends and will be coming very, very handy. And because we want to do this now separately, I am going to first use something what is called group by. So I am going to here use just a printout. So I'm not going to put a name on what I'm going to on this entity that I'm going to create. So I'm going to just use my dataset as a starting point, and I'm going to build some functions on top of this with a pipe. So first of all, I want that what I'm going to do is going to be done separately for the validation set and for the training set. So we have to split this data, but only for the calculation part. So this is why I'm going to use something which is called group by. So I want that R would make me two groups, one of the validation data and one of the training data. And I need to specify which column it needs to use to bring this, to create these two groups. And this, of course, is going to be the split here. This tells us which data was used for the training and which not. And then I need to also tell it what it should do. So I would like it to summarize for all of these points, or over all of these data points, what was the root mean square error. So I use a summarize function, and I say that I would like it to summarize to me a root mean square error. And to calculate this, there is a root mean square error function in caret package. And it wants two inputs. It wants predicted and it wants observed. And we can say the observed ones are the retention times, and the predicted ones are the RT pred. And now actually comically, we also want to the R to finish the grouping, so finish this splitting into two parts, or looking at two sets, the validation and training separately, and print us everything. So we need to always finish a command that has a group by with an ungroup. This is a bit counterintuitive at the beginning, but it takes a bit of remembering that every group by, when we split the data for a while, we also need to ungroup it. And now when I'm executing this, I will get a nice summary table about saying me what splits I had. So I had false and true, and giving me the root mean square error separately for both the training set and the test set. And now we can analyze this in the context of the requirement, what we actually want from our method and how good it should be, and if there is any overfitting to this.